Hi everyone, I am Manoj, PGT Physics, Sainik School, Kazhakootam. You are most welcome to our studio classroom, which we have settled recently. Today I am standing before you to discuss a very simple and interesting topic in physics. So for inviting your attention, I would like to demonstrate a very small thing. All of you listen this. This is a paper strip. Now, normally the paper strip will be like this. The task is this. Without touching here, see, without bringing like this, without touching, without a contact force, is there any possibility for bringing this in this level? Some of you may be having that idea, but I will demonstrate. See this. Without touching, how can it be brought in horizontal pattern? Just see it. See, I am going to repeat once more. I didn't touch. I have just blown some air over this paper strip. Then there is an uplift. Something pushed this strip to this position. What may be that? And what is the principle lying behind this? Let us see. And that principle is known as the world famous Bernoulli's principle. It is the Bernoulli's principle. So, what is the principle behind that? Of course, it is depending on the flow of liquids and gases. For example, you imagine a liquid is flowing through a pipe like this. A liquid is flowing through a pipe, a non-uniform pipe. That means the area of cross section is different. You take three positions here. See, this is the first portion of area A1, let this be A2 and let this be A3 and so on. It is going. But wherever you take the liquid, it will be associated with three forms of energy. Which are the three forms of energy associated with a flowing liquid? That I would like to tell you now. That is the first one is, the first energy is kinetic energy. And all of you know kinetic energy is half mv square. Next is the potential energy. Potential energy, you know, it is nothing but mgh. The third is the pressure energy. Pressure energy. How will you represent pressure energy? It is pressure into, when a compression is exerted, there will be a change in volume, there will be a corresponding change in volume in liquid or in gases, and that change in volume, let it be delta V, then the pressure energy will be noted as P into delta V. The Bernoulli's principle says that the sum of these energies per unit mass, it will be a constant. The sum of kinetic energy, potential energy and pressure energy per unit mass will be a constant. So, how can we write that? It is like this: half mv squared by m, that is a kinetic energy per unit mass, plus mgh by m, that is the potential energy per unit mass. Then the last one, P delta V by m, that is the pressure energy per unit mass. Bernoulli's principle says that wherever you are taking the flow of the liquid, these sum of these three quantities will be a constant. Here m and m will cancel, this m will cancel, and here it is volume by mass. You know, volume by mass, here volume by mass, it is nothing but 1 by density, where rho is the density. So, let us substitute all these things, what you will get? Finally, the equation is forming in this pattern, V squared by 2 plus GH plus P by rho is equal to a constant. See this. This is known as the Bernoulli's equation. So, what is the concept behind this? When a liquid is flowing, it will be associated with three forms of energy, which are kinetic, potential and pressure. The sum of kinetic energy, potential energy and pressure energy per unit mass, it will be a constant. Then you will get an equation like this, V squared by 2 plus GH plus P by rho is equal to K, and this is known as the Bernoulli's equation. Now, how is this coming? How can this be derived? So, we are going to see the derivation of Bernoulli's equation. Dear all, now we are going to see the proof of the Bernoulli's theorem. So, for that, you just imagine a non-uniform pipe like this. Through this pipe, a liquid is made to flow from bottom to the top. Naturally, a liquid will not flow like this. So, you have to apply a pressure. So, P1 is the pressure applied in this area of cross section, which is having a magnitude A1. So, P1 is the pressure applied in this area of cross section A1. Now, the liquid is flowing and there is another area of cross section A2. When the liquid is reaching there, the pressure is P2. So, here what is the pressure energy applied? The pressure energy applied is P1 minus P2 into delta V. P1 minus P2 into delta V, that much energy we applied in this tube. So, due to that, what happened? The liquid moved. That means there is a change in kinetic energy. At the same time, the liquid reached to another level from H1 to H2. So, the potential energy has increased. So, in short, what happened? When we applied the pressure energy, that pressure energy is utilized for changing the kinetic energy and potential energy. Let us see the change in kinetic energy and potential energy here. This pressure energy is equal to the change in kinetic energy is half m V2 squared minus half m V1 squared. This is the change in kinetic energy, where V2 is the velocity at the shorter end and V1 is the velocity at the bigger end. So, this is the change in kinetic energy. Plus one more, what is the change in potential energy? Potential energy here is mgh2 minus mgh1. So, the pressure energy applied is utilized for changing the kinetic energy and changing the potential energy. Let us simplify this equation like this, that is P1 minus P2 into, see, P1 minus P2 into volume. Volume is mass by density. So, P1 minus P2 into m by rho is equal to, and what is this? M is a common factor here, m into V2 squared by 2 minus V1 squared by 2 plus, here also one m is there, m into GH2 minus GH1. So, this m is getting cancelled. So, the further simplifications will be coming like this, that is P1 minus P2 by rho is equal to V2 squared by 2 minus V1 squared by 2 plus GH2 minus GH1. Up to that, is it clear to you? Now again we are going to arrange the terms. Just see, P1 by rho minus P2 by rho is equal to V2 squared by 2 minus V1 squared by 2 plus GH2 minus GH1. Now in this equation you see there are terms mixed as first condition and second condition. We are going to arrange the first terms and second terms separate. That means like this, that is P1 by rho. Now this V1 squared by 2 can be brought here, that is plus V1 squared by 2 plus GH1 is equal to, now we are arranging the second terms at the right hand side, that is P2 by rho plus V2 squared by 2 plus GH2. So in short, what is this? The sum of kinetic energy, potential energy and pressure energy per unit mass in the first condition is exactly equal to that for the second condition. So in general, what we can write here, that is V squared by 2 plus GH plus P by rho is equal to K. This is the proof of Bernoulli's theorem. Okay, till now you have seen what is the Bernoulli's equation and what is its proof. Now I would like to tell you one thing, that is the Bernoulli's equation for a horizontal flow. How is it coming? Just see, generally the Bernoulli's equation is this, V squared by 2 plus GH plus P by rho is equal to K. This is the Bernoulli's equation. Now see the headline, it is going to be applied for a horizontal flow. When horizontal flow is concerned, the gravitational head, that means this H is constant, this H. So this term is coming as a constant. So in general, what is that? V squared by 2 plus P by rho is equal to K. This is the equation for the horizontal flow. Now why I am telling this? At the beginning, I have shown you a demonstration, that is a paper strip. See, I have blown air like this. When air is moving like this, the velocity will be more. When velocity is more, you see this one, when velocity is more, then the pressure should be less, because the sum is a constant. V squared by 2 plus P by rho is a constant. So when I am in this equation, when I am blowing air, the velocity will increase. When velocity is increasing, automatically the pressure in this region will decrease. So here pressure is decreasing, so there is a suction. That means the lower pressure will be lifting the paper piece like this. See the demo. Like this. So when velocity is more, pressure will be less. So from the bottom, it will be lifting, the high pressure will be lifting the paper piece in this level. So, that was the reason. And this equation is applied in many situations as the applications of Bernoulli's theorem. There are so many areas for applying the Bernoulli's theorem that we will see one by one. Well, for observing the applications of Bernoulli's theorem, you have to know a small concept when the liquids are flowing through non-uniform pipes or tubes, and that is called as equation for continuity. See here, there is a non-uniform pipe through which a liquid is flowing. When a liquid is flowing, the rate of flow should be a constant because the liquid is not stagnated. There will not be any compressions or expansions here. So, the rate of flow throughout the tube should be a constant. That means rate of flow is a constant. What is rate of flow? Volume by time. So, volume by time should be a constant. What is volume? Volume is nothing but area into distance divided by time should be a constant. What is distance by time? This term, that is nothing but velocity. So, when you observe flow of a liquid through a tube, the product of area and velocity will be a constant. A into V is equal to K. Here you see, here it is A1 V1 rate of flow, here in this section it is A2 V2, and here it is A3 V3, and so on. So, in all situations, the product of area and velocity is a constant. So, the product of area and velocity is a constant, and this equation is known as the equation for continuity, and this can be seen, or it can be taken for observing the applications of Bernoulli's theorem. Okay, you have seen what is the equation for continuity, and we are going to see the applications of Bernoulli's theorem by implementing the equation for continuity. See, one of the most important application of Bernoulli's theorem is the Venturi meter. What is this Venturi meter? See, it is a device which is used for measuring rate of flow of liquids. Of course, when the flow is very less, the rate of flow can be measured by some handy instruments like beakers and all. But when fluid flow is very high, for example, suppose the shutter of a dam is opened, then the hydro engineers, they should know that how much water is going through 1 second. That means the rate of flow of liquid should be measured. This kind of huge rate of flow of liquids can be measured using an instrument called Venturi meter. See the structure of a Venturi meter. This is a schematic diagram of the Venturi meter. There are two big tubes, and these two tubes are connected to a small tube, and the small tube is called as constriction. And for these two tubes, there are two upper limbs. Now, a liquid flow is maintained in that. See, a liquid is flowing. Capital A is the area of cross section of the bigger pipe, and small a is the area of cross section of the smaller pipe. Now, when the liquid is flowing, you know that when area is more, then the velocity will be less. So, V1 is the velocity of the liquid in the first pipe, and V2 is the velocity of the liquid in the second pipe. Okay. What is the equation for continuity here? It is capital A into V1 is equal to small a into V2. Therefore, the velocity in the second pipe we can write like this, that is V2 is equal to capital A V1 by small a. Let it be equation 1. So, we have applied the equation for continuity in this particular situation. Now, coming to the Bernoulli's theorem, you see it is a horizontal flow. For a horizontal flow, we can avoid the gravitational head, that is GH. Then what is the Bernoulli's equation for the horizontal flow? That is V squared by 2 plus P by rho is equal to constant. And this can be applied in this tube. That is V1 squared by 2 plus P1 by rho is equal to V2 squared by 2 plus P2 by rho. Now, instead of V2, we have found one equation, the first case equation 1. Equation 1 can be substituted here. That is V1 squared by 2 plus P1 by rho is equal to, what is equation 1? Equation 1 is A V1 by small a. Instead of V2, A V1 by small a should be given. That is A squared V1 squared by A squared into 2 plus P2 by rho. This is the equation. Then from this equation, we are going to separate the pressure difference. That is P1 by rho minus P2 by rho is equal to A squared V1 squared by 2A squared minus V1 squared by 2. So, here V1 squared by 2 can be taken as the common factor, that is P1 minus P2 by rho. P1 minus P2 by rho is equal to V1 squared by 2 into capital A squared by small a squared minus 1. Again, simplifying P1 minus P2 by rho. What is P1 minus P2 by rho? It is H rho G. H rho G by rho is equal to, see here, in this venturimeter, when the liquid is flowing, here the pressure is more because the velocity is less, pressure is more. Because of the high pressure, the liquid is rising up to this level. But in the second pipe, the velocity is high, so the pressure is low by the Bernoulli's theorem. So, the liquid level will be less. So, these two differences will be noted as H. That is why P1 minus P2 is expressed as H rho G. So, H rho G is equal to V1 squared by 2 into simplifying A square minus A square by small a square. So, from this equation, we are going to find V1. See, one row can be cancelled. We will find the value of V1. Just see. So, cross multiplying, what you will get? That is 2A square into Hg. 2A square into Hg is equal to V1 squared into A squared minus A squared. See, from this equation, what is V1 squared? Therefore, V1 squared is equal to 2A square Hg by A square minus A square. This is a mathematical simplification, and finally, our idea is to find V1. Therefore, V1 is equal to square root of this quantity. So, A square is a perfect square. So, A into root of 2Hg by A squared minus A squared. See, this is the equation for velocity of the fluid in the bigger pipe. Now, I told you, what's our aim? Our aim is to find the rate of flow of the liquid through this pipe. So, what's the equation for the rate of flow? According to the equation for continuity, rate of flow is equal to, see, rate of flow is equal to area of cross section into velocity. Capital A V1 or small a V2, here we have found V1. So, the rate of flow can be found like this, that is rate of flow Q is equal to, let it be Q, Q is equal to capital A into V1. So, capital A into V1 is small a into root of 2Hg by A square minus A square. All of you concentrate in that equation. Rate of flow is equal to capital A into small a into root of 2Hg by A square minus A square. Here, except this value of H, all the other values are constants, because capital A is the area of cross section of the bigger pipe, small a is the area of cross section, and rho is the density. G is the acceleration due to gravity. So, all these things are constants. Therefore, Q is equal to a constant into root of H. See this? This is the principle of the Venturi meter. That means when liquid is flowing through a pipe, the height, that means there are two, as I told you earlier, there are two pipes, there is a height difference, and that will be calculated and it can be substituted in this equation. This is widely applied for finding the high rate of flow of the liquids. For example, recently in Mullaperiyar Dam, from the Mullaperiyar Dam, Tamil Nadu is carrying water. When they are taking water, it should be noted, that amount should be noted in terms of TMC. So, this kind of Venturi meters will be used for calculating the amount of water to flow. This Bernoulli's theorem is applied in some other situations also in our day-to-day life. For example, see, this is a thick bottle in which some liquids are taken. For example, let it be a paint. We are going to spray paint something. Then this bottle will be connected to a particular piston like this. This is a cylinder with a piston. This is a small hole which is known as the nozzle. This is the nozzle. So, what is happening? We are continuously moving the piston very fast. When you are moving the piston very fast, air will flow with a high velocity here. When velocity is very high, the liquid will rise from the bottle to this portion, and finally it will move along with air. So, when this liquid is coming along with air, it will be sprayed in all directions. See? And this principle is also used in atomic sprayer. High flow of air will be sucking liquids and it will be carrying along with the flow. So, this is one principle of Bernoulli's theorem. Now, one more application is there, just see. Normally, if you are looking the cross section of the wings of aircrafts, it is in a particular shape. For example, see, you see this? This is the cross section of the wing of an aircraft. Well, consider the aircraft is moving like this from your right to left. You see the air current. Air is moving in this pattern. See, look. When the wing is moving from your right to left, then air is moving in the opposite direction. At the bottom of the wing, the velocity is minimum. See, here the velocity of the air current is minimum. But what is happening at the top? Because of this particular shape, see, there is a shape, a curved shape for this wing. So, velocity is maximum here. So, at the two portions, bottom and top, the velocity difference is maintained by the air. So, according to Bernoulli's principle, here the pressure will be maximum and here the pressure will be minimum. When velocity is more, when velocity is more, the pressure will be less. So, always there will be a holding That means there is an upthrust, there is a high pressure to maintain the aircraft in air, and it's also depending on the Bernoulli's principle. Now at last, there are some beautiful scenes you have seen in TVs and all. For example, in sports, in football matches, when a corner kick is taken from the corner of the football ground, without any force, the ball will be taking a curved path and entering in the goal post. And commonly this is known as banana kick. So what is happening? When the football is kicked, it is having its own turning in the atmosphere, and this particular phenomenon of turning of balls like this, that is called as Magnus effect. Magnus effect. In cricket also, when a ball is tossed and bowled, it will be having its own turning in air, and that is called as the googly. The cricket players may be knowing that. And finally, all these are by the principle of Bernoulli's theorem. And finally, you salute our nation. When our national flag is flying, you see, it is waving in the air. When air is blowing, the flag is waving. What is the reason for this? When air is flowing, in some area the pressure will be less. The other side pressure will be more. So there will be a push. But at the same time, the velocity of the air will decrease, and there the pressure will be more. So in the opposite direction there is a push. So this push-pull action will go on either side of the flag, and you can see the waving of the national flag. Finally, I wind up the class by telling that this Bernoulli's theorem is applied in many walks of our day-to-day life. Thank you.